Students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as semiconductors. Let's see how an N-type semiconductor looks like. N-type semiconductor. Let's see a crystal lattice of N-type semiconductor. Now you have two electrons that are shared here, two electrons. The sharing of electrons takes place. Right? So you have sharing of electrons taking place. So in which case, this is your germanium, electron pair is shared, germanium, electron pair is shared, So you have, this is your crystal lattice of an N-type semiconductor where you have germanium and a small amount of pentavalent impurity is added. Let's assume that the pentavalent impurity is arsenic. Now arsenic has 5 electrons, out of which 4 electrons will combine with the adjoining 4 germanium atoms. One arsenic electron is going to be free. One of this electron is going to be free. This is my free electron that remains here. That means every impurity gives rise to one free electron. Every impurity gives rise to one free electron, and hence the number of electrons go on increasing. Right? As a result of which the negative charge, the number of free electrons go on increasing, which then constitute current in an N-type semiconductor, right? So what is an N-type semiconductor? When a small amount of pentavalent impurity is added to a pure semiconductor, it is known as N-type semiconductor. Right? So what is an N-type semiconductor? A pentavalent impurity added to a semiconductor will give you an N-type semiconductor. Now we are taking a very typical example where I am going to add arsenic or antimony, which are the 5th elements in the periodic table. So consider arsenic added to germanium. Right? Now germanium has 4 valency electrons. Germanium has 4 valency electrons. Right? When a small amount of pentavalent impurity like arsenic is added to germanium crystal, large number of free electrons become available. When a small amount of impurity like arsenic is added to germanium, when a small amount of impurity like arsenic is added to germanium, large number of free electrons become large number of free electrons become available. Large number of free electrons become available. Why? The reason is arsenic is pentavalent, that is, its atom has 5 valency electrons. As arsenic atom fits into the germanium crystal, 4 of its valency electrons form strong covalent bonds with 4 neighboring germanium atoms, and the 5th valency electron of the arsenic has no place in the covalent bond, and thus it is set free. That is the reason why you have large number of free electrons produced when arsenic is added to germanium, right? Now, I can say that arsenic has 5 valency electrons. Arsenic has 5 valency electrons. An arsenic atom fits into the germanium crystal. An arsenic atom fits into the germanium crystal in such a way that its 4 valency electron, that its 4 valency electrons form strong covalent bonds, with 4 neighboring germanium atoms. With 4 neighboring germanium atoms. Right? The 5th valency electron in the arsenic has no place in the covalent bond. The 5th valency electron of arsenic atom finds no place in the covalent bond. Finds no place in the covalent bond, and thus it is set free. Right? Therefore, for each arsenic atom added, one free electron will be available in germanium crystal. One free electron will be available in germanium crystal. Right? Though each arsenic atom provides only one free electron, yet an extremely small amount of arsenic impurities can provide enough atoms to supply millions of free electrons. Though each arsenic atom provides only one free electron, yet an extremely small amount of arsenic impurity a small amount of arsenic impurity provides enough atoms provides enough atoms to supply millions of electrons, right? And thus the germanium crystal doped in such a way acts as a good conductor. Thus a germanium crystal doped in such a way acts as a conductor. So now do we understand why a germanium crystal acts like a conductor? Right? So now when potential difference is applied, to the n-type semiconductor, you would have free electrons in the crystal that would be directed towards the positive terminal, which will constitute electric current. Thus, current conduction in n-type semiconductor is predominantly due to free electrons, and that is one of the reasons why it is called as an n-type semiconductor. I can say when potential difference is applied across an n-type semiconductor, free electrons in the crystal will be directed towards the positive terminal, The free electrons in the crystal will be directed towards the positive terminal, constituting electric current. Right? Thus, current conduction in an n-type semiconductor. Is predominantly by free electrons. Right? And therefore it is called as an n-type semiconductor. Therefore it is called as an n-type semiconductor. So do we understand n-type semiconductor? You have a pentavalent impurity added, which increases the number of negative charge, which causes the electrons to flow when potential difference is applied. So what are the important things that you need to remember about an n-type semiconductor? In an n-type semiconductor, it is the pentavalent impurity that produces an n-type semiconductor. The pentavalent impurity is called as the donor impurity, right? The pentavalent impurity produces the n-type semiconductor because it donates free electrons to the semiconductor crystal, right? Many new free electrons are produced by addition of pentavalent impurity. The thermal energy of room temperature generates a few electron hole pairs, but the number of free electrons produced by the pentavalent impurity far exceeds the amount of holes produced due to the breaking of the covalent bond, and hence the conduction of current is predominantly due to the free electrons that are produced. Fine, do you get this thing clear? As n-type semiconductor has large number of free electrons and very few small holes, a free electron in n-type semiconductor are considered as majority carriers. So the majority carriers are the electrons, right? So do we understand n-type semiconductor? Next, let's move to p-type semiconductor. Now, let's see the working of a p-type semiconductor. Now in a p-type semiconductor, let's first see a crystal lattice of a p-type semiconductor. In a p-type semiconductor, you would have a trivalent impurity that would be added. Now, since a trivalent impurity would be added, 3 valency electrons of the trivalent impurity would satisfy 3 covalent bonds, and there would be an empty space which is referred to as a hole where there should have been an electron, and this empty space is going to be my carrier of current, right? So this is, say, germanium. So my majority carriers are electrons. Sorry, my majority carriers here are going to be holes. This is that empty space which is referred to as a hole. Fine. So your current is going to be conducted due to the hole. This is your hole due to which the current is going to be conducted. Fine. Do we get this in here? Here we are going to add a trivalent impurity. The trivalent impurity that I am going to add is, say, gallium. Gallium is the trivalent impurity that I am going to add. So let's consider a p-type semiconductor when a small amount of trivalent impurity is added to a pure semiconductor, it is a p-type semiconductor. It is a p-type semiconductor. Fine, do we get this in here? Now, what we are going to do is we will consider gallium added to germanium. We are going to consider gallium added to germanium. Now, gallium has 3 valency electrons. Gallium has 3 valency electrons, right? So when a small amount of impurity like gallium is added to germanium, when a small amount of impurity like gallium is added to germanium, large number of holes will become available. You would have large number of holes that would become available. Large number of holes will become available. Right? Do we get this in here? Now, gallium has 3 valency electrons. Right? Gallium has 3 valency electrons. Hence, a gallium atom fits into the germanium crystal in such a way, gallium atom fits into the germanium crystal in such a way, it fits into the germanium crystal in such a way that its 3 valency electron, form strong covalent bonds, with 3 neighboring three neighboring germanium atoms. So you have three very strong covalent bonds formed. Now, in the fourth covalent bond, only germanium atom contributes the valency electron, whereas gallium has no valency electron to contribute. In the fourth covalent bond, I can say that only germanium atom contributes a valency electron, where gallium has no valency electron to contribute. Right? Now, as the fourth bond is incomplete, being short of one electron, I can say thus the fourth bond is incomplete, being short of one electron. Now this missing electron is called as a hole. This missing electron is called as a hole. Fine, do we get this in here? Thus each gallium atom added, one hole is created. Therefore, for each gallium atom added, one hole is created. Right? Yet an extremely small amount of gallium impurity provides enough number of atoms to supply millions of holes. Yet a small amount of impurity added provides enough atoms to supply millions of holes. Right? Now when current conduction in a p-type semiconductor takes place, that is thus when a germanium crystal is doped in such a way that it acts as a conductor. Now when potential difference is applied to a p-type semiconductor, free holes in the crystal are directed towards the negative terminal constituting current. Before that I can say thus a germanium crystal doped in such a way acts as a conductor. Right? Now when potential difference is applied across a p-type semiconductor, free holes in the crystal are directed towards the negative terminal constituting current. right? Thus current conduction in a p-type semiconductor is predominantly due to free holes. Thus current conduction in a p-type semiconductor is predominantly by free holes, right? And therefore it is called as a p-type semiconductor. Therefore it is called as a p-type semiconductor, right? Do we understand this? So what is a p-type semiconductor? When a trivalent impurity, or it's a trivalent impurity that produces a p-type semiconductor, right? Now the trivalent impurity which produces the p-type semiconductor is known as an acceptor impurity, right? The pentavalent impurity was known as the donor impurity. The trivalent impurity is known as an acceptor impurity. Why? Because it produces holes that can accept electrons. The new holes are produced by addition of the trivalent impurity. Thermal energy of the room temperature generates a few amount of electron hole pairs, but the number of holes produced by the trivalent impurity far exceed the number of holes and electrons produced by the breaking of the covalent bonds. Therefore, there is a predominance of holes over electron in a p-type semiconductor. Thus, a p-type semiconductor has large number of holes and small number of electrons. The holes in the p-type semiconductor can be therefore considered as majority carriers because they are the ones that are going to carry current. Fine, do we get this thing clear? Next, let's consider a p-n junction. Right? What do we understand by p-n junction? First, let's see the construction of a p-n junction. Now, when a p-type semiconductor is suitably joined with an n-type semiconductor, the contact surface is called as a p-n junction, and such an arrangement is called as a p-n junction diode. Right? So, merely joining two pieces of p and n-type semiconductors, because the surface film cannot form a p-n junction because the surface film and the other irregularities will produce major discontinuity between the two crystals. So I just cannot take two crystals and join it. What I have to do is I've got to fuse one crystal into the other, right? So hence a p-n junction is formed from a thin crystal of semiconductor by diffusing the p-type material on one half side and the n-type material on the other half side, and then connecting wires to the p and the n-type crystals, and then the whole crystal is then sealed in a plastic casing, right? That's how a p-n junction is produced. Fine, do we get this thing here? So what is p-n junction? When a p-type semiconductor is suitably joined to an n-type semiconductor, when a p-type semiconductor is suitably joined to an n-type semiconductor, the contact surface is called as a p-n junction. The contact surface is called as a p-n junction. The contact surface is called as a p-n junction, and the arrangement is called as a p-n junction diode. And the arrangement is called as a PN junction diode. Fine, do you get this in clear? Now, how is this done? A PN junction diode is formed from a thin crystal of semiconductor. A PN junction diode is formed from a thin crystal of semiconductor by diffusing the p-type material on one half side by diffusing the p-type material on one half side and the n-type material on the other half side. Right? Connecting wires are attached to the P and the N region and the crystal is then covered. Connecting wires are attached to the P and N type and the crystal is covered in plastic material Fine, do we get this in clear? Now, a PN junction diode is also called as a junction diode, or it is also called as a semiconductor diode, or it is also called as a solid state diode. How does it look like? You would have a crystal. Half of the crystal is doped with P-type semiconductor. The other half of the crystal is doped with N-type semiconductor, and you have connecting wires coming out from either side. The P-type region is called as the anode, and the N-type region is called as the cathode. Right? And the diagram for this, symbolic structure for this is going to be this. This is the symbol for a PN junction diode. This is going to be my anode, and this is your cathode. So that's your construction of a PN junction diode. Fine, do you get this thing clear? Now, let's see how a PN junction diode produces a potential barrier. Now, let's consider a PN junction diode. Let us consider a P-type material has high concentration of holes and N-type material has high concentration of free electrons. Right? Hence, there is a tendency of holes to diffuse over to the N-type free electrons. We know that opposite charges attract. Now see this. This is my PN junction diode. This was the actual barrier between the PN junction, right? Let's assume that these are my holes here. Let's assume I have electrons on the other side. This is my P type, and this is N type. You have electrons here. Now, at the intersection of the P and the N junction, there will be a tendency for the electrons to diffuse over from the N type over to the P side, because opposite charges attract. As a free electron moves across the junction from N type to P type, the P type hole gets uncovered. Therefore, you would have some electrons that would come here, and you would have some holes that would go on to the other side. Right? So you would have electrons moving into the P-type semiconductor, and you would have holes moving into the N-type semiconductor. Now, as electrons move into the P-type semiconductor, they will go and sit into the holes. Therefore, where I had a charge carrier, I will now have a neutral carrier. Right? Similarly, on the N-type semiconductor, you would have electrons will go and sit into the hole. So instead of having a charge carrier of electron, now I'm going to have a neutral carrier. Now the second layer of electrons will not be able to jump and go on to the P-type semiconductor. Why? Because now there is a barrier, there is a neutral barrier between them. Initially, the P and the N-type semiconductor were connected to each other, so there was no barrier between them. It was very easy for the holes to jump into the N-type semiconductor and the electrons to jump into the P-type semiconductor. Right? Hence, a negative charge is going to be built up. A negative charge is going to be built up on a P-type region, where now when sufficient charges are built up, the negative charge on the P-type region will then start repelling the electrons that are coming from the N-type region. I have a negative charge that is built up over here. Now this, we know that like charges repel, so the next set of electrons that try to come into the P-type region, they are going to be repelled. They are going to be repelled by this barrier of electron over here. Similarly, the next set of holes that try to go into the N-type region are going to be repelled by the holes. Fine, do we get this thing clear? Thus, a barrier is created against further movement of holes and electron, and this barrier is called as a potential barrier or a junction barrier. Right? Do we get this thing clear? So this here shows this is nothing but the migrated electrons from N-type. Migrated electrons from N-type. This is nothing but the migrated holes from P-type. Migrated holes from P-type. Right? Now this is the space from here to here. This whole thing. This is going to be the space which is going to be called as the depletion region. Right? So this particular space is called as the depletion layer. This is my depletion layer. Now as a result of this depletion layer, an electron that tries to move from the N-type to P-type will have to overcome this depletion barrier. Hence, a certain amount of potential will have to be provided to those electrons to move from the N-type semiconductor to the P-type semiconductor, and that particular potential is called as the potential barrier. Fine, do we get this thing clear? Right? So let's see the formation of potential barrier. Right, consider a PN junction. Right, let's consider a PN junction. Now, the P-type material has high concentration of holes and the N-type material has high concentration of free electrons. The P-type material has high concentration of holes and the N-type material has high concentration of electrons, right? Hence, there is a tendency for the holes to diffuse over to the there is a tendency for the holes from the p type to diffuse over to the n type, and free electrons from the n type to diffuse over to the p side. Hence, there is a tendency for holes to diffuse over to n type and electrons to diffuse over to p side. Fine, do we get this thing clear? Now, this process is called as diffusion. This process is called as diffusion, right? This process is called as diffusion. Now, as the free electrons move across the junction from n type to p type, the donor ions are uncovered, that is, they lose their electrons. As free electrons move from n type to p type, region, from the n type region to the p type region, the donor ions, that's your p type holes, right? The donor ions are uncovered, that is, the donor ions are uncovered, that means they lose their charge, right? This leaves behind positive immobile ions in the n-type semiconductor. This leaves behind positive immobile ions in the n-type semiconductor. Obviously, as the electrons are now fitted into the holes, you would have uncharged ions, and these are your immobile ions that are sitting there. Similarly, the movement of the holes from the p type to the n type, similarly, the movement of the holes from the p type to the n type, the movement of the holes from the p type to the n type leaves behind a negative immobile ion, leaves behind a negative immobile ion, leaves behind negative immobile ions on the p side. Right? Now, hence a negative charge is built on the p side. Hence, a negative charge is built on the p side. Fine, do we get this thing here? Now, when sufficient charges are built up, when sufficient charges are built up, on the the negative charge on the p side, the negative charge on the p side, repels the free electrons. The free electrons to enter from N type to P type, to enter from N type to P type. The electrons now, because of the like charges, electrons can now not enter from the N type to the P type. Similarly, positive charge on the N type. Similarly, positive charge on the N type. Positive charge on the N type repels holes to enter. Repels holes to enter. Repels holes to enter from P type to N type. From P type to N type. Right? Thus a barrier is set up against further movement of holes and electrons. Thus a barrier is set up. A barrier is set up against further movement of holes and electrons from holes and electrons. This is called as potential barrier. This is called as potential barrier. This particular barrier is called as potential barrier. Fine, do we get this thing clear? Now, do we understand how a potential barrier is made? The potential barrier, it should be noted that outside the barrier, on both sides of the junction, the material is still neutral. Only inside the barrier there is a positive charge on the N type and a negative charge on the P type, and this region is called as the depletion region. I can say that inside the barrier, there is a positive charge. There is a positive charge on N side and negative charge on P side. Right? This region is called depletion region. Fine, do we get this thing clear? So do we understand how a potential barrier is created and what is a depletion region? Right? Okay, we'll stop this here for the day. Thank you very much.